In section 9.5, we'll be talking about series. This is a finite arithmetic series. It's finite because there's only 4 terms. There's not an ellipsis after it saying it'll go on forever. It's arithmetic because there's a common difference, in this case of positive 8. And it's a series because we have plus signs in between the terms, as opposed to commas, which would make it a sequence. We're going to write the explicit equation for the sequence of these 4 numbers if there had been commas. And the first term, A1, is 11. If there were a term 0, we would back up a common difference and we would land on the number 3. This is like the y-intercept. If we're going to write a y equals mx plus b equation, y is replaced by a sub n, x is replaced by n, m is replaced by the common difference, and there's our y-intercept, a theoretical term 0. That's just a quick way to write the equation without going through the whole point-slope form and distributing. Back up one term. We'll put that explicit formula in sigma notation of the explicit formula as some letter. I'm going to use the letter K. We could use the letter I or J, typical letters, goes from 1 to 4. When K is 1, I get 11. When K is 2, I get 19, etc. When K is 4, I get my last term, which is 35. I will call this the sum of the first 4 terms of the series, S4, and it'll equal this answer. But what if I make this into an infinite arithmetic series by adding 3 dots? If I was to add all of these terms, it would diverge. I would go to infinity. But what if I just want the first 100 terms? The sum of the first 100 terms. There's my notation right there. And it is sometimes called a partial sum, since there's an infinite number of terms, and I only want a sum of the first 100. Well, I could set up my notation, S100, sum of the first 100. I could set up my sigma notation, but I'm not going to plug in 1 and 2 and 3 all the way up to 100. That's way too much work. There has to be an easier way. Notice that I can write out the sum of the first 100 terms. That's the first plus the second plus the third term plus ... In this case means just keep on going all the way till these last few. So not forever, just up till here, 98, 99, 100. Of course, I could switch it around the other way and start with 100, 99, 98, etc., etc. And then, in this case, if I actually plug in 1, 2, 3, and 98, 99, 100, I get these numbers. And you can see that when I add down each column, I get the same exact result each time. So here, if I add down, I get 2 sums of the first 100 terms. And what I get here is 100 answers of 814. So here I have my 100 answers of 814. I'll divide both sides by 2 to solve for S100. So that particular answer is 40,700. That's what the first 100 terms add up to. But even better than that, I now have a formula that I can use based off of this process here, which I can use for any arithmetic finite series and get an answer. 100 because there's 100 terms. Divide by 2 because I had 2 sums that I used in my little strategy here. 814, that's it's the first term plus the last term. It's also the second term plus the second to the last term, or the third plus the third to the last. But for simplicity, it's the first times the last, or the first times first plus the 100th here. So I have the first term plus the 100th term. So here's a formula I can use for any number of terms that I would like to add up. So what we said is that if you add up an infinite number of terms and sum them together, the limit as n approaches infinity, as you get more and more terms and start to approach an infinite number of terms, it will diverge. You'll just get a bigger and bigger answer. Whatever letter you use at the bottom has to be the letter that you use in the explicit formula. This letter at the top is a number. In this case, it's a number that gets closer and closer to infinity. In this case down here, the number at the top is 100, so it's a finite arithmetic series, and that will have an answer. But you need to have three things. You need to know how many terms there are, you need to have the first term, and you need to have the nth term or the 100th term. Then you can do it. Okay, so now we have two formulas for arithmetic. We have one for the sequence and one for the series. And of course the way that it'll work now is that you'll be given a problem and you won't have everything that you need, and so you've got to find something before you can find the final answer. Same over here. In both of these cases, we don't know how many terms there are. We know the first term, we know the last term. We don't know how many there are. So in our formula for sum, I don't know what the n is. Same for this one here. I know what the sum is, actually. I know what the first term and the last term are. First term and the nth term. But again, I don't know how many terms there are. Notice that there's an overlap between these two formulas. They both have a sub n in them, and they both have n in them. So we can use these like a system of equations. Or we could use the explicit equation to find something that we don't know, like n, and use it then substituted into the s of n equation. In the first case, I don't know my n value, so I'll use my explicit equation. I'll find my common difference, which is 3. I'll find my theoretical term 0, which is my y-intercept. I'll write mx plus b. Common difference times n plus a0. Then I can plug in my last term and solve for n, and that tells me how many terms there are. Now I can take that number, 233, and plug it in for how many terms there are. Now I know I'm finding the sum, the partial sum, of the first 233 terms, and I can do it on my calculator. In the second case, I don't know n, but I have enough information right here in my sum equation to solve for n. So in this particular case, with what was given, I have 27 terms that start with A1 and go to A27 and go for a distance of 104. So that's 104 difference in the two y values and 26 difference in my two x values, 27 minus 1. So my common difference, my slope, is 4. And now I can use my explicit equation with my common difference and my n value that I'm desired for finding here, 15, plus my theoretical term 0, which would be 4 back from our first term because I am going up higher and higher, so go back from there. And I can figure out what term 15 is equal to. So I'm using these two equations together to answer questions where there's just not quite enough information given. In this next example, we're going to talk about an alternating arithmetic series. It's not really an arithmetic series because it's not changing by the same amount each time, but if the minus signs weren't there, it would be. So it's an alternating series that would be arithmetic if the minuses weren't there. I can either list out a few terms of the thing and then put the general term. This is the term that would represent any of these terms, depending on what n is equal to. And notice it's n plus 1 for the power, so that when n is 1 for the first term, it's positive. Or I could use set notation with the squiggly brackets and just put the general term in there, and that could represent the set of all the numbers that are in the series. I want to find the partial sum of the first 100 terms. In this particular case, we do not need the formula that we got before. This is easier. The reason it's easier is that every two terms, when put next to each other, equal to -8. every pair of terms. So how many pairs would there be, or how many negative eighths would there be, in the first 100 terms? The other main type of sequence that we talked about in section 9.4 was the geometric sequence, and that is when you have an explicit formula, a general term formula, that looks exponential, like a times b to a power. So we are going to talk about how to sum up the terms in a finite geometric sequence, so that'd be a geometric series. And again, we could plug in 1 and plug in 2 and plug in 3 all the way up to 12 and add up all the answers together, but there's an easier way. Notice that I can write out all the terms in the sigma notation. I've skipped a few, but I put the first 3 and I put the 12th one in there. And then I can multiply all of those terms times this b value. So that's 1/2 times the original summation. So half of this is here, half of this is here. And a half of 64 is 32, and a half of 1/8 is 1/16. Then when I subtract down, all these middle terms cancel out. And I have this minus this, everything else is gone. And I have one summation minus this many summations. And I can get my answer. But even more importantly, I now have a formula. Where did this come from? It was 1 minus the r value. I know it's the a times b, but in this case for sequences and series, that multiplier is our common ratio, so we use r to stand for that. So that's 1 sum minus the ratio. That's what we have right here. Then I have the first term, and I have not the last term, but the one past that. Okay, but notice for the first term we multiply by r, or rather for the second term we multiply by r. For the third term we multiply by r squared, not to the third power. So this term that's one beyond is where we multiply by r n times. So I have the first term minus one beyond the last term, or the first term minus the first term times r to the nth power. I can factor out the a minus 1. I can divide by 1 minus r, and I have a formula that I can use for any finite geometric series. If I know the first term, the common ratio, or the growth amount, and how many terms there are. But here's something even better. What if instead of the first 12 terms, I want to know what all of the terms add up to? That means the limit as n approaches infinity from I equals 1 to n of this. So an infinite number of terms. Now if it was arithmetic it would diverge. But if it's geometric and the r value is a fraction, I will be able to get an answer. Notice that if the r value is a fraction, like 1/2, and I take it to a really large power, a half to the millionth power, or to the infinite power, that becomes 0 whenever that's a fraction. So really my numerator is just a1 times 1 over 1 minus r. I have a shortened formula that I can use when r is a fraction to find the sum of an infinite geometric series, which in this case is 512. Here are the formulas we've done in this video for a finite arithmetic series, infinite arithmetic series, no answer. Finite geometric, infinite geometric, where the r value is a fraction, so it could be a positive or negative fraction. If the r value is greater than or equal to 1, then it diverges.